This episode we're looking at a French startup called Sail'nFly, who have just published footage of their RCO2 demonstrator making its first successful flight. And there's a lot to unpack in this footage, because this skim machine has some interesting design choices. Welcome back to a new episode of One Wing Spin Above, where we discuss anything to do with ground effect. My name is Paul Dutch. Sail'nFly was founded in 2021 by 3 engineers who, between them, cover both sides of what you need to build a skim machine properly. Marc Maynard is a naval architect, Sébastien Raymond is an aeronautical engineer, and Stéphane Aubin, also aeronautical. He brings ground effect specific experience to the team. He was also the one responsible for the EAGS 2001 conference that we have covered here before. A quick footnote here by the way of declaration. I know Stefan since we worked together assisting Edwin van Opsal on the WIG page. The WIG page was a big database of ground effect machines that no longer exists. The team doesn't stop there, as there are other shareholders in the company that joined later. That's the kind of team you want. Naval architects who know what happens when the hull hits a wave at speed, and aeronautical engineers who know what happens when the wing stops working. And they have a lot of supporting experts in technology and markets. A lot of skim machine projects have stumbled because they were one or the other. The company is based in France, and their stated goal is commercial WIG transport, port to port, fast, low emissions. The RCO2 is a 2-meter remote control demonstrator. It was tested in March 2026, and the company reports successful validation of takeoff, maneuvering, and obstacle avoidance. So this is a proof of concept phase. They're not testing passenger comfort or certification paperwork. They're asking whether the design actually flies the way the simulations said it would. And apparently it does. Now 2 meters is small. At this scale you're really validating aerodynamic and hydrodynamic concepts, not structural or propulsion systems. But that's fine, that's what this stage is for. What's interesting is that even at this scale, the RCO2 is clearly a detailed representation of the intended full-scale design. The hull shape, the empennage, the float arrangement, these are not simplified for the model. You can see the design intent clearly, which makes the footage generally worth analyzing. So let's look at 3 things: the hull, the floats, and the tail. The hull is a conventional planing hull shape for a skim machine, which is to say it's designed to transition cleanly from displacement through planing and into the air without the bow digging in or the stern catching spray. But look at the aft end. The hull extends well behind the wing trailing edge in a long tapered tail section. The reason for this is what happens at the moment of liftoff. When a ground effect craft transitions from the water surface into ground effect flight, it pitches up. The cushion builds under the wing, the nose comes up, and if nothing corrects that, you end up climbing out of ground effect, which is exactly where you don't want to be. The extended hull aft acts as a lever. As the nose pitches up, the tail raises, that long hull extension behind the center of gravity swings down towards the water surface, the proximity increases the dynamic loading on the tail, and the pitch up is arrested. The vehicle settles back into the ground effect regime faster than it would with a shorter hull. It's a passive pitch recovery mechanism built into the geometry. This is an elegant solution because it doesn't require additional control inputs or active systems. The hull shape does the work automatically during that critical liftoff transition. It does add length and some weight, but what you get in return is a more forgiving and more stable entry into ground effect flight. Now the floats. You can see clearly that the wingtip floats on the RCO2 have what look like foam block extensions added to the existing float structure. They look like they were put there during the test campaign, not designed from the start. This is completely normal at prototype stage, and it's not a sign that something went wrong. What it tells you is that they went out on the water, did some runs, and found that the original float volume wasn't quite enough for the lateral stability they needed. Maybe a wing was dipping, maybe turns were too twitchy, so they added buoyancy fast. The thing about wingtip floats on a wig is that you're always making a compromise. More float volume means more drag, and it means disrupting the span-wise flow near the wingtip, which is exactly the zone where ground effect is doing a lot of its work. Less float volume and you've got a machine that wants to roll over in crosswinds or during water turns. So you test, you iterate, and that's what the foam blocks are. For a production vehicle, these would obviously be designed properly with hydrodynamic shaping, but at the RCO2 stage, cutting gluing foam to add buoyancy quickly and test the difference is exactly the right approach. The tail is where this design gets interesting. There are a lot of surfaces back there. You've got one horizontal stabilizer on what appears to be twin angled vertical rudders, but then there are some additional surfaces. This looks like it may include end plates on the horizontal tail. So why does a skim machine need so much tail? The core issue is pitch stability. In ground effect, your main wing's lift curve slope is different from what it is out of ground effect. As the vehicle climbs slightly, say due to a gust or control input, the wing moves out of ground effect, lift drops, and if you don't have sufficient pitch down restoring moment, you can end up in an oscillation. This is the height instability problem that has troubled skim machine designers since the Alexeyev's era. The traditional solution, which this design appears to be using, is to put the horizontal tail high and far aft, so that it sits largely outside ground effect and its lift curve slope remains relatively constant regardless of the main wing's height. That gives you a stable trim condition where the tail is always pushing with a predictable force while the main wing is doing most of the work in the cushion. The additional surfaces, the end plates, are likely there to increase the tail's aerodynamic effectiveness without having to make the entire structure larger for flight. Specifically weathercocking, which is where REGENT struggled as well. REGENT converted their conventional tail to a box structure. It is where at low speeds in the water, the wind pushes onto the tail and wants to point the craft into the wind, regardless of where the pilot wants to go. There are two big flaps on the tails to ensure roll and pitch for the sake of simplicity. At the prototype stage, they may also be doing some explanatory work, testing different configurations to see which gives the best balance of authority and drag. They're still finding the right configuration. That's good, that's what a demonstrator should be doing. The craft is using computer-controlled flight system, which is a simpler version of what REGENT are using. This is for simplicity purposes and to ease the pilot workload. It is said that the early Aeroplans were really hard work to fly so close to the surface, even though they were stable in ground effect. A computer can take the strain out of the piloting of the craft. So, if the RCO2 validates the concept, what is the actual product? Sail'nFly announced two initial variants under the name Seagull. The Seagull 4/6 is 11.35 meters long, 9.6 meters wide, with 184 kilowatts of power, 4 to 6 passengers, 100 kilometers an hour cruise, and roughly 90 minutes of range. This is the taxi class vehicle. Island hops, harbour connectors, short coastal routes. They also mention a VIP configuration. At 180 km an hour on a 90-minute tank, there's theoretically up to 270 km of range, enough for Nice to Bastia, Dublin to Holyhead, and that sort of route. The Seagull 8/9 scales it up, 18.10 meters long, 16 meters wide, 515 kilowatts, 9 passengers, same 180 kilometers an hour cruise, but over 5 hours of autonomy. That range opens up longer routes. Helsinki to Tallinn in under 30 minutes, Abu Dhabi to Doha in under 2 hours. Where does this sit compared to other skim machines we've covered? Sail'nFly are going with conventional propulsion and a planing hull, which puts them closer to the Airfish 8 lineage than to REGENT's hydrofoil and fly-by-wire approach. That's a more conservative choice technically, but it may also be a more practical one for a startup working with limited capital. Fewer moving parts in the certification puzzle. The question, as always, is whether they can get from a 2-meter RC demonstrator to a crude prototype with enough funding and enough operator interest to define the final design. Sail'nFly say they're actively looking for operators to co-develop the production version. Before we wrap up, it's worth comparing the Seagull to a skim machine that tried to solve a very similar problem about 20 years earlier, the Seafalcon, from the German company Meerestechnik out of Rostock. The Seafalcon was also an 8-seater, built from fiberglass composites, to keep the weight down, and also aimed at short coastal and island hop routes. It was tested from late 2006 on the Warnow River and then out to the Baltic near Warnemünde. Power came from 2 diesel engines, Mercedes A-class units, about 100 kilowatts each, so roughly 200 kilowatts total. Claimed top speed was around 150 kilometers an hour. Compare that to the Seagull 8/9, 550 kilowatts, 180 kilometers an hour, more than double the power for the same passenger count, and 30 kilometers an hour faster. Part of the difference is almost certainly down to advances in lightweight construction and propulsion efficiency over 2 decades. But it also suggests the Seagull is targeting a more aggressive performance envelope. The Seafalcon story is also a useful cautionary tale. A test flight in 2007 ended in an accident, which effectively finished MTE. The rights sat dormant until Seafalcon picked them up in 2014, but as far as anyone knows, the program has never returned to active development. One bad day on the water and a promising skim machine program was over. That is not unique to the Seafalcon. The skim machine space has a long history of prototypes that flew, had a problem, and never recovered. It's one of the reasons the RCO2 test campaign matters. Sail'nFly getting a demonstrator through takeoff, maneuvering, and obstacle avoidance without incident is generally an important milestone, not just a box-ticking exercise. So, Sail'nFly, a strong team, a credible design, and a prototype that, on the footage, is doing what it's supposed to do. The hull extension makes sense, the foam floats are exactly what you expect from an honest test campaign, and the complex tail tells you they're working on a real problem and haven't assumed it's solved. I'll be keeping an eye on this one. Drop a comment if you have thoughts on the design. Particularly curious about what you make about the tail arrangement. Links to the Sail'nFly website and the RCO2 test footage are in the description. For now, thank you for watching. Keep in the loop by hitting that subscribe button, and we'll see you here for the next episode of One Wingspan Above. Keep on skimming.